So I'd like to introduce Mr. Lou Turnello from Cadence.
Thank you, Sean. Good afternoon. So today I'm going to talk to you about picking the right DDR IP for you, for your projects, for your systems, for what you're working on. So first, you have to start off with understanding what your system requirements are. Forget about the IP for a minute. Let's talk about what your requirements are. What type of DRAM do you need for your particular applications? So in this slide here, I have 5 different application segments, starting with storage, networking, consumer, industrial, and mobile. And each of them traditionally have used, if you see on the left over here, these are the types of DRAMs that they've traditionally used in the past. And then what I'm showing over here on the right of the arrow is the new DRAMs that they're going to be migrating to. And typically, the migrations are because of a number of reasons. One, cost. DRAM is a commodity-driven business, and so typically when you have higher volumes, the price points of the DRAM devices go down. So as you introduce newer DRAMs, when they get to high volume, typically the prices go down. So cost is one motivation. Typically, new generations of DRAM have higher density, and typically they have higher performance. So that's why you'll be transitioning. But some of the key requirements for each of these application segments I listed over here, and you can see depending on which application segment, your requirements are obviously different, and so you have to consider that when you're selecting the type of memory device that you're going to be using. So let's combine storage and networking here for a moment. So in the RAID storage or solid state drive or even networking domains, density, which is the amount of memory a system has, is one of the key requirements. They have a lot of traffic that they run and a lot of data that has to be stored. So density is one key requirement. Performance is typically number 2. Again, moving from DDR3 to DDR4, the motivation is also higher performance, not just higher density. And then power, right? So these systems are pretty heavy-duty systems. They're not typically low-margin products, typically higher margin products, lower volume, higher margin products. And so they burn a lot of power because they have a lot of interfaces, a lot of SerDes, a lot of DDR. And so these are typically the top 3 for those particular application segments. And moving down the line here, we have consumer. And consumer, high definition television, cameras, displays, set-top boxes, anything you consider a consumer that's not mobile. We'll put that over here in the mobile category. And number 1 criteria is cost. You go out there's a lot of high definition televisions out there. Do you pick Vizio, LG, Samsung? Who knows, right? So there's performance benefits, and they try on features and performance, but the big thing is, can they make margins on their product? So cost is number 1. And traditionally, what I refer to as PC DRAM, which is the DDR DRAM, because of the volumes that have been shipped, driven by the PC business, the price points of those devices go down, and so typically DDR DRAMs are cheaper than LPDDR. So that's one of the main motivations for the consumer space to be selecting those DRAMs. And then you have industrial, medical, and then finally mobile. And mobile, it's pretty obvious. We say power is number 1, and that's what drives into these DRAMs. And the reason for that is, so these DRAMs cost more. They're value-added DRAMs. They have a lot of very low power features, and that's what's driving power. And then performance is the second one. So you think of mobile, you think of battery, you may not always think of performance, right? Well, let's look at what we have today. You have the iPhone 6. You have the different tablets in the industry today. How many applications can you run at one time in an iPhone 6 or a Samsung Galaxy S6? Quite a few. And so actually, the S6 came out, and I heard that the S6 is shipping with LPDDR4. So performance is number 2. And then third, last but not least, is cost, because they have to make a margin. They have to make a profit on these products. So first thing is understanding what your application space requires, the type of DRAM that you need, and then obviously equating that to the IP, making sure the IP supports that. So that's kind of step one. So you start there. The next is more of from a technical implementation perspective. It's like, okay, so I have this IP, and your data sheet says it'll work at 2.4 gig or 3.2 gigabits per second or what have you, but so is it going to work in my system? Once I put it in my package, on my board, talking to that DRAM, is it going to work? And so, being that it's an interface IP, which means it actually has to go off chip, there's a lot more involved. It's not just like a memory that's on chip or standard cells that are just talking to each other on chip, which is you can contain that in your design. You can control that. When you go off chip, there's a lot of other parameters that you have to consider. And one of the things that you have to consider is noise and how the noise affects the quality of that interface to be able to reliably transmit data from your chip to the DRAM and back and forth. And so, again, you have to, ideally, you'd like to see something like this where you don't have any jitter. That's in an ideal world, and let's be realistic, that probably won't happen. You will have some, but it's understanding what it is, where it is, and how to manage it. And so different things that you can do with that, controlling the power supply domains, whether you isolate the power supply domains, how you manage the clock network and the clock tree, the types of PLLs that are used in the IP to support that. So those are all key things that you want to consider when evaluating and selecting a DDR IP. Getting a little bit more specific now, this is talking about architecture. I'm going to talk about DDR4 first, and then I'm going to talk a little bit about LPDDR4. So what I'm showing here is different timing parameters, and don't worry about the big table here. I'll explain what this is and what to consider and look out for. So moving from DDR3 to DDR4, going from 2.1 gigabits per second to 3.2 from DDR3 to DDR4, it doesn't come for free. It adds complexity to the DRAM, and it adds architectural changes which impact the different timing parameters. So for DDR3, this table would be essentially basically one block for RRD and one block for CCD. But now DDR4, because of the complexities in going into higher data rate and in changing different configurations, you have different timing parameters. So you got to be cognizant of what you're getting into. So you move from DDR3 to DDR4, you want to make sure the IP can handle it. You want to make sure that your system can handle the types of traffic that's going to happen, and along with what to expect from a performance. And so what we're showing here, so RRD stands for row to row delay, and CCD stands for column to column or CAS to CAS. Essentially in the DRAM, it's an array, right? So you have rows that go, memory elements that go across in what's called a row, and then you access them with columns which come up and down. You've probably heard of a page. So your column access, that big section that you access from the row, that's called the page in the DRAM. And so the different timing parameters are how many clock cycles does it take to bring up a row or to activate a row and then to activate a column. Now, in a DDR4, everything works in what's called a burst length of 8, which is 4 clock cycles because it's a double data rate, so 2 bursts or two data transmissions every clock cycle. So 2 times 4 is 8, so a burst length of 8. So every one of these parameters you want to contain within that 4 clock cycles, because that means you can launch it and you can activate that and you can start reading before the other one finishes. So the number 4 is the magic number you want to see. So for a by 8 device, you have 4 cycles across for row-to-row delay. For the short. For the long, it increases 5 to 6 to 7 as you go higher in data rate. So obviously, when you get up here, you want to stay in this domain. And the same thing with the column delay. You want number 4 is the magic number. So as you go higher in data rate, or you have to go to a different region which uses this long parameter, then you have to be cognizant about that. So you want to make sure that your IP is going to look at it's going to understand the DRAM, understand the traffic coming in, and it's going to prioritize accesses with these timings. That's going to maximize your efficiency. Okay? So that's DDR4. Now let's look at LPDDR4. So LPDDR4, it supports data rates up to 3.2 also, so it's very high performance. Actually, LPDDR4 is the first low-power DRAM that's going to exceed PC DRAM data rates. So the present generation of DRAMs at LPDDR4 is 3.2. The next generation is going to be 4.2 gigabits. Now, if you think about that, if you know anything about SerDes interfaces, so SATA is 3 gig, USB is 480, USB 3 is 5 gig. So LPDDR4 4.2 gig, this is a 32 to 64-bit interface running at 4.2 gigatransfers as compared to a USB, which has a handful of pins running at 5. So it's quite a complex problem. But from a DRAM perspective, again, your row-to-row delay, you got your 4 cycles there. And remember we said the burst length, that's the key factor. So in LPDDR4, the burst length is 16, which is 8 clock cycles. So your magic number is indeed 8. And so what you would see here, I don't have a chart, table like this or an eye diagram like this for DDR4, but for the other timing diagrams, for the longer ones, you would see gaps here, which we call dead cycles, which is basically wasted bandwidth. But in LPDDR4, you don't see that. Okay, so there are other aspects of LPDDR4 from a density perspective that does not make it practical for high density applications like solid state drives and so forth. But from a performance perspective, DRAM developers did a really good job with this, hitting the high data rate and giving you good efficiency for the high speed mobile applications. Okay. So real quick summary, we talked about application space. What do you need? Do you need DDR? Do you need LPDDR? Do you need maybe options for both? Depending on if it's consumer, maybe you have a consumer product that's going to be in a cost sensitive that you want to use a PC DRAM, and that same chip's going to be used in maybe a low power where a high value added where you can get more margins where you might need a low power DRAM. So you want to consider that. What type of DRAM do I need? Does the IP need to support multiple protocols or not? The second is, does the IP really understand how those DRAMs work and to make sure you get your maximum throughput and efficiency in your system? Whether it's LP4 for mobile or GDR4 for solid state or consumer or what have you. Okay? So here is just kind of showing some test results that we have. So this is our DDR4 3200 product. We have it in the lab running at 3.2 gig. This is an eye diagram that you see. So a couple things pointing out here. So you see a little bit of jitter on the data, which is normal, but running at 3.2 gig with an eye that's this wide open this is pretty good. And this is a test chip, and this is in a board with the 2 DIMM slots with the furthest DIMM that's populated. And the other thing I want to point out is the DIMMs are not. So you can go on Amazon and you can find a 3.2 gig DIMM, but it's overclocked. You will not find one from Micron, you will not find one from Hynix, you will not find one from Samsung. They don't make them today because it's a tough problem to solve to support 3.2 gig in a heavily loaded DIMM environment. The most you'll see is 2400. They might start coming out with 2667. We're using a 2400 DIMM token to the memory manufacturer, and we're overclocking it to 3.2. So the other thing I also want to point out here is the types of margins like jitter specifications, duty cycle distortion that's allowed in the DRAM is directly related to the performance. So for a 1600, you're going to have more slop that you can allow, more margin, 2400 a little less, and 3200 even less. So our IP is running 3200 with the 2400 DIMM. Okay? Now this is LPDDR4. So you notice the previous one was in a DIMM environment because a lot of the applications using PC DRAMs are DIMM based. Whereas in LPDDR4, this is in a POP. POP stands for package on package. So I don't recommend you rip open your cell phones, but if you did, you would probably see a POP for small form factor, which is you have your SoC, which is your application processor, and it has a special package, and the DRAM is actually stacked right on top of it. And then typically the heatsink will go on top of that. And so what we've done is we specially designed this heatsink so we can stick probes in and actually make these measurements so we can actually measure and see what the waveforms look. But obviously in your cell phones, you're not going to see wires coming out of there. But again, you can see here running at 3.2 gig. This LPDDR4 is a 3.2 gig LPDDR4, so it is designed and manufactured to support 3.2. And the data eyes in our test vehicles are actually pretty good. I mean, the jitter is actually very low. Most applications, hopefully we can see this. You may not see it in all of them, but the good news is that there's a pretty wide data eye there, and you want to make sure that's there because from lot to lot, whether it's silicon, from board to board, there's variations, and you have to cover those. Okay. So this is a kind of a snapshot chart of the Cadence IP portfolio. So Cadence has been doing IP now for maybe about a decade. Really started in earnest 5 years ago, almost 5 years of the date when Cadence acquired Denali. And that started with the DRAM protocols and the storage. Since then, there's been a number of acquisitions, a lot of organic growth, and it's populated our IP portfolio to include everything that you see here. So we talked about DRAM and storage. We have display IP with HDMI. You probably heard of MIPI and SoundWire. USB, everybody's heard of USB. So 3.1 is 10 gig. So that's the next generation of USB. PCI Express for all you PC guys out there. Ethernet, and as well as analog mixed signal. So a number of different IPs in our portfolio today. So that concludes my presentation. So a quick summary, Cadence has a complete portfolio, so breaking it up, memory and storage, DDR, as well as SD, SDIO, eMMC. So those removable SD cards, that interface, Cadence develops the IP for that. NAND flash, interface, high-speed interfaces, so PCIe, PCI 2, 3, and 4, up to 16 gig. USB, up to 3.1, which is 10 gig. Ethernet, MIPI, HDMI. Everybody knows HDMI is that, and it has a high-def television or Blu-ray player. And then we have a lot of analog devices, right? So WiGig, LTE, A to D converters. And then we have these sensor monitors and timing circuitry. So these are not interface IP that you might be aware of, but these types of IPs are being used more and more because they give you visibility in what's happening in your silicon. So I talked about jitter in one of the previous slides as to how the power supply can contribute to jitter on your signals. The problem with our SoCs today is you can measure the power supply at the chip and on the board, but you don't know what's going on inside. So these monitors actually give you the ability to, you place them across your die, and you can monitor exactly what's going on with the power supply and the noise level. And then you can correlate that to what's happening in your chip. And that's going to give you the eyes inside the die to figure out what's going on. Multi-protocol SerDes, complete subsystem solutions. So it's not just a controller or PHY, but a complete subsystem. And then integrated with Cadence tools. So obviously being a tool company, all of our IP is developed with our own tool suite. And then Cadence is investing and expanding. So fastest growing IP provider since 2013. You saw the array of IP that we have today. Developing more and more IP and more process nodes. TSMC, you named the different foundries, and we have IP across a number of different foundry nodes. And we are also enlarging the IP ecosystem, in particular part here, being here in the chip talks with ChipEstimate to help proliferate the usage of our IP in the ecosystem. So that concludes my presentation. Are there any questions?
Any questions? Some of your customers that are currently using the IP is HiSilicon?
Yep, that was publicly announced. Yeah.
Oh, and Freescale?
Yes.
Okay.
Yeah, so HiSilicon is actually, I think this was publicly announced, they were the first semiconductor company that was manufacturing products on TSMC 16 FinFET, and they're using our DDR IP.
Very nice. Well, thanks, Lou. Thank you very, very
Marshall.
much. Lou Turnello, Cadence.